3 o'clock. Let's talk Kubernetes. And I want to get started fast, and I'm going to speak fast because I got way too much to cover. But I want to get it covered so that you understand it. So I'm going to give a little introduction to Kubernetes for developers. I am not going to look at any form of DevOps, CD, CI stuff at all. I want to show why Kubernetes is interesting, or rather how it's interesting for developers and what you need to know as a developer, because you can't just build an application and say, awesome, I have an app and now it's going to run in Kubernetes. We need to know what Kubernetes is and how it works. So my name is Klug. I work as a developer at a company called Active Solution in Stockholm. We do a bunch of cloud stuff. That's all I'm going to say. You don't need to know any more about me. I just need to say Active Solution one more time because they pay for me to go here, or they pay my salary while I'm here. So they're very nice to me. But this is the important stuff. Docker. So Docker is kind of the foundation of why I ended up doing Kubernetes. And containerization in general seems to be really, really popular right now. However, Docker, however awesome it is, has this little limitation. This is about what you can do with Docker. You can containerize your application. You can tell Docker, please, can you run this? Limit the amount of memory, limit the amount of CPU, and if it ever fails, restart it. That's it. That is not quite good enough for a production application. We probably want to have more out of it. And we could live with this, but there would be a lot of manual work involved. So we need orchestration. So I went online and I Googled orchestrate to get the definition of what it actually means. And it says, the first part, arrange or score this. Plan or coordinate the elements of a situation to produce a desired effect, especially something I'm not even going to try to pronounce. I am from Sweden. That is kind of what we want. We want to coordinate things. We want to build like a microservices architecture, potentially. We want to orchestrate a bunch of containers. It's orchestration. And then, really cool, when you Google a word, it gives you this little graph of how much that word has been used recently. And you look at the end there. We're hyping this now, because nobody's really cared about it until sort of 1900s, and then it got popular mid-1900s. And then at the end, we got it to swing up again because we're doing containerization and orchestrating things. Awesome, we are doing the cool new stuff. Then I clicked on the graph, and it looks like that, and it drops off at the end. So I'm too late into technology again. I don't really care that it's not the most latest and the greatest, but it's cool anyway. So Kubernetes is going to be what we're going to cover here. And I want to start with an overview, because Kubernetes, you can jump straight in and you can start hacking away on it, and you can get it to work probably with some introductions or demos and things like that. But I do actually want to cover what Kubernetes is doing. What are the building blocks involved in having Kubernetes run? What is Kubernetes? To me, that made a lot of sense. It was a lot of reading and figuring out how things were put together and how they work, because most people focus on how can I get my app running on Kubernetes, not what does Kubernetes actually do. But I'm the kind of person, I want to know what it does so that when it fails, I know how to fix it or abandon it and go somewhere else. So first of all, we have machines. I'm going to start very, very low level. We're going to have hardware. The difference between running your average application and running Kubernetes is that all of your machines are split into two groups. You're generally splitting them something like this. So there's going to be a few master nodes. So master nodes is what's called the control plane. That's where you tell it what to do and it orchestrates and gets things running. And it basically, that's where your logic lives and how you control your cluster. And then you have worker nodes. They used to be called minions, which is just so much better of a name. I'm going to pull up a new minion. Yes. Worker nodes or minions are basically your machines that will run your workloads. So you tell the master plane or the master nodes or the control plane that I want to run these nodes, and then these containers, and then they figure out how to get those containers spread across the different worker nodes in your cluster, so you get an even use of resources. They figure out if a node goes down, it gets rescheduled, and so on. So you've got those two different kinds of nodes. Unless you're running in a cloud, so if you're running on EKS or GKS or AKS, which is Amazon and Google and Azure, if you get a Kubernetes service from any of those, the control plane is not going to be one of your machines. So you don't have to put up your own machines for the master nodes. You've put up your worker nodes, but the master nodes is handled by the provider for you. So they will give you that control level, but then you pay for your actual nodes. So the control plane. The control plane is actually fairly simple, but it took a little while, at least for me. I might be really dumb, but it took me a while to figure out what was actually happening. So first of all, desired state. With Kubernetes, and when you talk to the Kubernetes cluster, you actually don't tell it that I want to run, hey, start up a container for me, please start this container for me, please do. What you do is you say, I want this to be my desired state. I would like there to be 3 containers running at any point of time. And then that's your desired state. And then it's up to Kubernetes to figure out that your 3 container instances are always running and they're nicely spread across the different worker nodes. So it's all about desired state, not about telling it, do this, do that. So the very, very, very high level overview of this is this. So the user comes in and it has a desired state configuration. That desired state configuration, which is generally kept in a YAML file, is pushed to a REST API. So it's sent up to the REST API. The connection is secure and all of that. But basically, you send it up to the REST API. The REST API, which is part of your control plane, takes that desired state configuration and puts it into a database. It's called etcd. It's a key value pair data store. That's it. Well, and actually, before I start, that's kind of what your big part of your control plane does. When you do that, it kind of ends there. Your interaction with Kubernetes ends at that point. Once that is in there, there is something in Kubernetes called the Kube Controller Manager that continuously asks the API, are there any changes? Has anything happened? And it will find out, it will get that new desired state, and it's going to go, yes, somebody told me that this is a new piece of state that we should handle. And the Kube Controller Manager, or actually the scheduler controller, there are quite a few different controllers running inside of it, but you can see a controller as a piece of software that basically just runs continuously in the cluster and the control plane to verify that changes end up doing something. So the scheduler controller will have a look at your desired state configuration to figure out that, hey, you told me to run 3 instances of this container. It then asks the API for the nodes in the cluster, basically what worker nodes do I have, and what are their current workloads, how much stuff is running on them right now. It figures out what nodes are relevant to run the new workloads, so it basically assigns different work node names to your desired state configuration and restores that state configuration in storage again. That's it. If you can stop here. If you only have master nodes, that's also going to happen. You're going to have stuff going in and out of a database. That's it. It does not go around telling anybody to do anything at all. It just adds stuff to the database. That's it. Then we have the worker nodes that are responsible for actually running our code or our workloads. And if we look at the worker nodes, they are just separate machines, but they're in the same network as your control plane. And they will be running some form of container runtime. Most people look at this and go, oh, Kubernetes runs Docker. Nope. Kubernetes can run Docker, and by default runs Docker, but it doesn't actually necessarily run Docker. You can run a few different container runtimes. And they're also making that a standard, so now you can go and say, I have a container runtime that adheres to this API, and then you can replace it. So a couple of options would be to run, instead of Docker, you can switch it out for CRI-O or Containerd. Containerd also happens to be the runtime for containers that runs inside of Docker. But it's a smaller version of Docker without a bunch of stuff that you don't need if you're not using Docker as Docker, but you're using Docker inside of a Kubernetes cluster. But basically, you have a container runtime that will run your containers. It will do the work for you. Then your worker node has something called a kubelet. A kubelet is a piece of code that runs on that worker node that knows how to talk to the control plane. So the kubelet continuously, just as the controllers on the master nodes was asking the API for changes, the kubelet asks the control plane or the REST API continuously, is there anything that should be scheduled on me? Is there anything that I should be running that I'm not running? Is there anything I should be running that I'm not running? Over and over and over again, until the control plane or the API goes back and says, yes, you should be running this node as well. Or sorry, you should be running this container as well. The kubelet then talks to the container runtime and tells the container runtime that, hey, can you please schedule these containers and run them for me? So Kubernetes doesn't do anything but tell Docker what to do, or the container runtime. So it's basically just a little managing thing that sits there and goes, you want me to run at least so many of these, I'll figure out where to run them, and then I'll make sure that they get scheduled on that. But it's still running, in this case, Docker, for example. So I'm going to show you that when I run Kubernetes on my machine, when I spin up a Docker container inside my Kubernetes cluster, I can see that in the regular Docker commands on my machine. So I can go and say Docker PS, and I can actually see the running containers. I can interact with them, and I can make changes to them. Kubernetes is just there on the side, helping us out to make sure that they run as they should. And finally, there's something called the kube proxy. The kube proxy is a way to manage communication inside the cluster. So whenever you want to talk inside of the cluster between different containers, you end up with the situation that your calls gets proxied through a kube proxy to make sure that, because you can't really take a dependency and say, I want to talk to container X because container X might or might not be there between two different calls. So to make that work, it always proxies through a proxy server that can handle the changes in containers coming and going continuously. That's it. Very high-level introduction. 11 minutes in, I'm done with my talk. I thought I'd actually give you some practical stuff as well. So we're going to look at the building blocks that we'll be building. Because the thing is, there are little things, there are like little blocks that we pull out and we go, I need one of those, I need one of those, I need one of those. We put them together like Legos, and all of a sudden we have a system. Kind of nice. And it's fast on top of that, which is cool. So the first thing I want to cover is the pod. I have been talking about running containers so far in my talk. You don't actually run containers in Kubernetes. You do under the hood. So low-level wise, yes, we are running containers on worker nodes in the cluster, but you cannot schedule a container or tell Kubernetes to run a container. You always tell it to run a pod. So a pod is the smallest unit that we can tell Kubernetes to work with. A pod contains one or more containers. That's about it. It is perfectly fine to have a pod with just one container in it, but the pod is the smallest thing. And the reason for a pod is that we often have this idea of containers working together. So if you put a container inside of the same pod, or multiple containers in the same pod, they will all have the same IP address. So they will share the same address namespace, but so they cannot expose the same port. But you can have as many containers as you want inside of the pod, and as long as none of them expose the same port as another container, you're good to go. That's fine. They also have the ability to communicate between each other with inter-process communication. So they can communicate in a different way than over the network like you normally would, because they're kind of processed together. And they can share storage. So if you set up storage inside of your pod, you can have all the containers in your pod, or some of them, read and write to the same storage, which could be really, really useful. And then you basically schedule pods in your application or in your Kubernetes cluster. That's the way it works. One thing to note, sorry, before I go to the next slide. It might seem obvious that certain things, oh, I'm going to put these containers together. Remember, when you combine containers into a pod, remember that they scale together. It's not a matter of how do I want to basically put this into production. It's more of a how do I want to scale this, because it does scale together. So it might seem obvious that, hey, I'm going to take my WordPress website and the database, and I'm going to put those two containers in the same pod because they belong together, so communication is going to be really quick between the database and the WordPress site, right? Until you start scaling up and you realize that you get one database per WordPress site or WordPress instance of your. So load balancing that would be a bit of a fail, because you'd basically add things to one and it wouldn't be available in the other. So every other time you refresh the web page, you would get some data, and then in some cases you would get some other data. It would kind of be a failure of websites, to be perfectly honest. But let's get a bit more practical. So how do we work with this? Now we know we have a pod, and we can schedule containers, or we can run containers based on pods. Well, first of all, how do we run it on our local machines? Well, if we want to run it on our local machines, you install Docker for desktop, which is the easiest way to get up. It works on Windows and Mac without a problem. On Linux, you can just run the Docker natively, but on Windows and Mac, you run this. And then you go into the settings and you tick that little thing that says enable Kubernetes, and all of a sudden your machine is now a one-node Kubernetes cluster with the master node and the worker node being the same node, which for production use is a big, big, big no-no. But for running locally on your machine, trying stuff out, it works fine. With that, you also get this cool little command called kubectl, kube control, or my personal favorite, kubectl. So kubectl is this tool that helps us talk to the REST API. We could build our own REST API client, but we'd have to implement security, so we need to implement authentication. But other than that, telling Kubernetes to do something is just a matter of posting or getting things in and out of a REST API. That's it. But kubectl will do that for you in a very, very nice way. And it's a very simple command. kubectl space, whatever you want to do. I want to get something, I want to delete something, I want to create something. And then the resource type that you want to do, so pod, for example. And then if you go with just that, kubectl get pods. By the way, the S at the end isn't mandatory. Actually, you can go kubectl get PO. That's enough for it to figure out that you want pods, and it will give you all the pods back. That will give you a list of all running pods in your cluster. Not quite, but ish. And this will give you a specific pod. So this will give you the information about the pod called my pod. So now you know how to use kubectl. That's all you need. If you want to create something, you can call the create command, or most people just go with apply. Apply works both for creation and updates, so it's like a create update command. And you call kubectl apply -f, telling it that I have a file, and here is my YAML file that contains my configuration, and you just call that, and all of a sudden there's some stuff running in your cluster. Piece of cake. It also has one other cool feature, and that is port forwarding. The problem, not the problem, but one of the things with the way that Kubernetes and also Docker works, to be honest, is that everything you put into Kubernetes works in its own network area, right? So it's a separate network from your local machine. Even though I'm running Docker for desktop on my machine, Docker actually runs currently, in this version, inside of a Linux VM that runs in Hyper-V. So it runs in a completely separate thing, so I can't just go and say, hey, go to my browser and go localhost port 80 and it's going to hit my container. That's just the way it works. So what kubectl offers is port forwarding. So what we can say here is, hey, kubectl, can you please port forward port 8080 on my local machine to port 80 inside of the pod called my pod? And then while that is running, it basically locks the thread on that. While that is running, you can then go to your browser and just go http:// localhost port 8080, and you go straight into it. And it's so cool, it's actually transparent enough that I've done this talk once before, or a couple of times before, but I did it in Stockholm, and I did the whole talk, and there was one little demo that failed. I couldn't explain why I couldn't see a container running in my cluster in my local Docker stuff. So I went Docker PS and I couldn't see my container, and I was like, weird, I don't know quite why. Probably some weird configuration thing. And then I realized the day after that I had run my entire presentation in a cluster in Azure instead of my local machine because I had forgotten to switch clusters. But with port forwarding, it doesn't matter if I'm port forwarding locally on my machine or I'm port forwarding into a data center in Ireland where my cluster is running. It just works, which was really, really cool, to me at least. So how do we create a pod? I have a bit of code here. So I have this simple, stupid application. The application So I didn't want to show you any code because I thought that was too complicated for you. So I was kind of wondering if everything else works. Did I screw something up?
Should be all right.
This is when I wish I could tap dance or sing or something to entertain you while he was fixing it, but trust me, you don't want to hear me sing. Something is, there it is.
Got it?
Yes. What, did I do something wrong?
Nope, it's fine. Don't worry about it.
It's fine, don't worry about it. That is AV tech code for, yes, you idiot, you did, but I fixed it. Okay, there is an app in here. The app is just a pure ASP.NET Core application. It doesn't, what it does is not important. The code is here, and you can download that code if you want to have a look at it. It's on GitHub, I think. Otherwise, I'll put it there. So I have this thing, and if you want to run a pod, you can either do that, which I guess is a bit small for you to read in the back. You could go and do this. kubectl run generator run-pod/v1 web app image blah blah blah, and if you do that, it will start a pod for you without you having to create a YAML file. I have done this command exactly once in my entire career, and that is because I wanted to see if it worked. After that, we don't do that anymore. Because what we want to do is we want to create these files instead. So this is a YAML file that defines a pod. So it defines what I want to run inside of my pod. And it starts out with saying, what API version am I using, v1? There are a bunch of different ones. Depending on the resource type you're creating, you need to figure out what API version you're in, whatever. What you do is you go to Google and you go, Kubernetes pod YAML example. And then you take that and you copy it and then you modify it to what you need. That's what I do, at least. It works perfectly fine, unless you can remember all the different versions in your head. You tell it what kind it is, it's a pod. And you give it some metadata. In this case, I'm giving it a name, web app. So that's the way that if I want to go and look at it, I can go kubectl get and then web app, and it will give me my, or get pod web app. I have some labels. I'll get back to labels later on. Ignore it. There's a spec in here. So the specification tells the system, for this pod, what is it that I really want to run? And in this case, I'm telling it that I want to run one container. It's going to be called web app. Name of the container doesn't really matter that much. I give it an image. So this is the Docker image that I want to run. Right now, I'm hosting it in my Azure Kubernetes or Docker container registry, or image registry. And I tell it image pull policy is just when you pull this, because I'm not going to be responsible for doing the pulling, so I'm not going to go Docker pull. Instead, Kubernetes is going to do it for us, or the kubelet is going to tell Kubernetes to do it. I want to tell it to make sure that that happens at a reasonable time. So always is good, because you don't end up with, if you do things like pushing the same image with the same name and the same tags, for example, then always will sort that out. I might have done that once or twice. So doing it always kind of solves you from that problem, but you can also tell it to only pull if it's not available and so on, so it can be a bit optimized. Then you tell it what ports you want to bind, so I want to have port 80 on my container, so basically give me port 80 bound to my pod. Resources, I'm going to tell it that, just as I can with Docker, that you don't get to use more than, I need 64 megs of memory, and I need 1/4 of a core. The CPU thing depends on where you're deploying it. If you're deploying on a local hardware with an Intel processor, this I think means 1/4 of a hyperthread. But if you push it to Azure, it becomes 1/4 of a virtual core. So it kind of depends on where you end up. But it's a resource limitation saying I need at least 1/4 of a core. And for memory, I'm also saying that I'm not allowed to use more than 128 megs. If you go above 128 megs, you're doing something wrong. Kill the container and restart it for me. And the same thing for CPU. If you use more than half a core, then it's actually going to go above in some cases, and it probably won't get killed, but I'm trying to limit the CPU usage as well. One thing to note here, if you start doing this locally and you have a little microservices architecture that you want to run on your machine, and you give every little service 1/4 of a core, very, very fast you'll realize that you don't have a lot of cores on your machine, and it stops deploying stuff for you. So these limits are great to have in production. When you're running on your local machine, these will kind of kill you once you get up to a few pods on your machine. And finally, since there is security involved, I need to tell Kubernetes how to pull my image. I've told it that the image is available at katesfordevs.azure.cr.io, but that is a private repo, so I need to give it credentials, and normally you would do Docker login, right? But once again, we are not pulling it, Kubernetes is. So the way that we tell Kubernetes to pull an image that is in a private repo is that we put a secret, which is a username and a password, inside of the cluster, and then we tell the cluster that you can find the username and password in a secret called katesfordevs, and then that is inside of your cluster, so that whenever I push a pod or apply a pod, it will go and use those credentials for my access. So having that up, we can go out here. I'm in that same folder. We'll do kubectl apply-f, like that. Open this up so I remember what to do. It's up and running. We do kubectl get pods. You can see that there is a 1 pod up here. There's 1 out of 1 ready because I only pulled up 1 pod. It is running. It has 0 restarts, and it was 8 seconds since I started it when I did the get command. Then we can say kubectl port-forward web app 8080 port 80, like that. It looks up here, and if I pull up my browser, we go localhost port, not that, port 8080. That is my application, up and running. And if I go out here and I kill my port forwarding, I try to refresh this, it doesn't respond, so I'm not faking this. I was actually talking to my pod. And also, kind of interesting, or not interesting, but semi-interesting is that is my pod running in Docker. So once again, Kubernetes is not something that is separate from anything else. It just automates creation of things in my Docker container runtime, which means that since this Docker container runtime is running on my machine, I can see all the pods that are up and running, or all the containers in different pods running on my machine at the moment. We'll do kubectl delete pod web app, and now it's gone. Nope, that would have been cool if that worked. There it is, now it's gone. There is a graceful shutdown period for Docker images or Docker containers, so an ASP.NET Core application does take a few seconds to basically die. That is running a pod. That's as simple as it is. It takes a few seconds to get started with running with Kubernetes on your machine. Install Docker for desktop, tick that little box, and you're up and running with doing at least pods to begin with. However, you should never create pods like that, like I just did. So why did I show you? I don't know. It felt like a good place to start. And it's a thing you do. You often pull up a pod just to see that stuff works, but we shouldn't use pods manually, because if you do, if you want to do a load balanced environment, then you're kind of screwed, because now if you want to have 2 pods, 2 instances running, you will have to go and do kubectl apply. You're going to have 2 different YAML files, because they do need to have different names, because otherwise it's just going to be considered an update to the previous one. So you need 1 YAML file for each instance of your pod that you want to run, and then you have to cross your fingers that they are put onto different worker nodes, because if you decide that you want to have 3 replicas, having 3 replicas on 1 node is just dumb. So you want to use something called a replica set. No, the picture has nothing to do with the topic, but it was a cute picture. But before we can get started, so replica sets is basically a way for me to deploy something to my Kubernetes cluster and say, I want to have a set of replicas, and I want to have 4 instances running, for example. And if you don't find 4 instances, then please spin up enough to see that there are 4 instances. But if there are more than 4 instances, please go and kill the ones that shouldn't be there. However, before we get started, there's one thing we kind of need to figure out, because just getting started with replica sets without thinking is bad. It's going to end up with that. We need to understand labels. I mentioned when you saw my pod that there in my pod YAML there was a little labels thing that I said you should ignore. Labels are really cool because anything in Kubernetes, any resource that you create in Kubernetes can have a label or multiple labels. Labels are literally key value pairs in strings. So it's a key and a value. They're both strings. You can add them to your metadata for your resource, and then you can use that to find different things. So if you have 600 pods running in your cluster, you can go and say, please get all the pods where the label X equals Y. Okay, why is this important? Because that's the way the replica sets work. Replica sets don't own any pods at all. So when you create a replica set, they don't own any pods. When they create a new pod, they don't own it. So instead, what they do is they have a label selector that basically says, I want to have at least X amount of pods running in my cluster with the corresponding set of labels. That allows us to be very, very flexible, because I don't tell you how you need to organize your pods and the labels and how to find them and everything. It's up to you. You can do whatever scheme you want. It's really, really flexible and very simple. It also means that if you set up a pod on your own with basically just start a pod for me, and you happen to have the same label set that your replica set requires, if you add a replica set after the fact that you created your pod first, your replica set will adopt that pod because it just happens to have the same label set. It doesn't really care whether or not it is the same pod. It will just adopt that thing. And if it doesn't find enough pods with that label set that you have told it, or that label selector, it will go and create new pods based on the specification that you've told it. Basically a template saying, here is my pod template. If you don't find enough pods, this is the template you should use. So if we have a look at that, it looks like this. No, not at all. It looks like replica set. There it is. It looks like this. So a replica set is in API version apps/v1. It's called a replica set. When you're doing kubectl or kube control, you can call it RS instead of replica set, because replica set is really long. You give it a name, you give it a label. This label here is just information about my replica set. Has nothing to do with the other labels I was talking about. This is just a way for me to find replica sets based on labels if I wanted to do. And here is my specification for my replica set. I want to run 3 instances of my pod. And the selector is this, match labels. I want to have 3 pods in my application, or in my cluster running that has the label app set to web. If you don't find 3 replicas with that, here is a pod template. This part here from row 13 and down is an exact copy of the pod YAML I just showed you for the pod. It's just you put one level on top of it. And obviously, the label set for your template has to correspond to your label selector. Because if it didn't, it would mean that, hey, I can't find enough pods, schedule a new pod. Hey, I can't find enough pods, schedule a new pod. Hey, I can't find a pod, schedule a new... It's going to suck. And also, there is built-in security for that. So if you try, I did the other day by mistake, it actually tells you that they don't correspond, so it's not going to work. So it's going to fail when you try to. But if I take this here, we go back out here, we go to my replica sets, we do kubectl apply -f that goes up. We do kubectl get all. So get all will give you all resources, which is not true at all. It will give you all of your pods and your services and your replica sets and a few other things, but it won't actually give you all resources. There's a limited set that you get back. But this is the interesting part that I want to say. Replica set, desired 3, current 3, ready 3, age 4 seconds. So I know that they're all up and running, and I can see there are 3 pods up here running. The cool thing here is that if we do this, we do that, and we start another one of these. We put that on the side there. That, we do CLS there. We can go and do, that was not what I wanted. kubectl get pods -- I thought I wanted to show you something. I did, there it is. -- watch. This is going to show me pods, but it's also going to stay here. So you see it locks up the terminal. What it does, it watches for changes. If I go back out here and we say kubectl get pods, if I could spell, I'm from Sweden, I can't spell. kubectl delete pod, and we want the pod, let's take that pod. You are going to die, my friend. There it is. As I killed that pod, you can see on this side here, my pod went into terminating state. Once that goes into terminating state, all of a sudden there's a new one that basically spins up straight away. So that goes into terminating, that goes into pending, then creating, terminating, 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 running. And now, if I go and look at the end result of that, I really cannot get this right. Yes, I know, set alias K, which is awesome because you don't have to write kubectl, but I wanted everybody to see that I'm typing kubectl all the time and not K. But there, in the end, this is what we end up at. As you can see, the T44FM has been transformed into another pod. So whenever I kill a pod, another pod gets added. If I were to manually create another pod, it would kill that pod for me. And the replica set just basically keeps everything in check for me. And if you ever want to remove a pod from a replica set, for example, you have a misbehaving pod that you don't want to kill, you want to debug it, you just go in and you update that pod and change the label set for it so that it doesn't fit into the replica set anymore. Then all of a sudden your replica set is going to spin up a new pod to replace the one that just died or disappeared, and you can keep on debugging your pod that was misbehaving, for example. But now we have a problem. Because now we have multiple pods, and we want to be able to load balance them. But we cannot talk to them right now, because now we have multiple pods that are coming and going, so I don't have an endpoint to communicate with. And that's why we need something called services. So a service in Kubernetes is a really weird thing. It doesn't actually create anything. It's a resource you create in your cluster that says, I want to have a unique endpoint in my cluster that I can call, and it will then use that to figure out what pods I should be targeting and load balance across the pods that matches the services, once again, label selector. So a service is basically a fixed point where I can reach a set of pods based on their label selector. And the cool thing here is that the label selector doesn't need to target a specific type of pod. You could have multiple different types of pod with the same labels, and your service would basically randomly send you to different types of pods, which is awesome and also really, really scary and hard to do something useful with, but it would be kind of useful in some cases, I think. So what is a service? Well, I'm going to go out here. I'm going to show you. Services are cool. I did leave my replica set up and running, so I still have a bunch of pods in here. But I can't talk to them unless I choose a specific pod. So what I've got here is I've got a service. This is my service here. Very simple. So app version v1, it's a service. It has a name. It has a spec. So it's a cluster IP service. There are a couple of different types of services. This is a cluster IP one, which gives you a virtual IP address inside of the cluster. And whenever you call that virtual IP, you end up at this service here. And that then causes you to proxy through the kube proxy and a few networky thingies that we don't need to get into. But basically, it gets a virtual IP address that we can use. It uses a selector. In this case, I'm selecting all of the pods that I currently have running, because they all have the label app set to web. And I'm saying that, hey, I want you to listen for TCP connections. I want you to listen for port 80, and I want to forward it to port 80 on the pods that I have selected. Take that, go back out here. Do that, kubectl get all. You'll see here now that I have another service. There's always a service in your cluster called Kubernetes. And the name of your service is also a DNS entry. So you can just go inside of your cluster, you could just go and do an HTTP call or REST call to http://Kubernetes, and that would end up at the Kubernetes API is on the control plane. But I got one called web here. It's got a cluster IP, which is 10.108.46.150. I don't really care. But we can say kubectl port-forward service web app. Was it called web app? what's it called, web only, 8080 port 80. Yes, there's a slash in there. There it is. If I go back out here, press refresh, ta-da! I'm now talking to my service, which is awesomely enough load balancing, not at all. That is because it's actually not talking to the service. The way that port forward works in Kubernetes is that it chooses the first IP address in the matched pods and port forwards to that specific pod. So it doesn't go through the service because that has to go through the kube proxy and a few things, so it just selects one pod. But you can use it to basically say, I want to talk to one of the pods in this thing here, and internally in your cluster, talking to that endpoint would cause you to talk to a random set of your pods. I'm just going to go and delete that. I don't need that anymore, and we'll do kubectl delete rs web app. And now my cluster should be empty. Yep, all gone. So services are kind of cool. They are essential for you to communicate with your pods. You can never talk pod to pod because they might come and go. Services will give you a fixed place. Also, you cannot actually really find your pods. Pods don't get specific IP addresses. They get random IP addresses. So there's no way for you to really initiate pod-to-pod communication in a very simple way. They are a little bit more complicated though, and that's the fact that you can go and create different types of services. You can have something called a node service, for example, that will bind a port on each one of your nodes in your cluster and then forward that port to the set of pods, for example. That allows you to basically have an entry point entry application through any of your nodes, which you can then load balance with a load balancer in front of it, for example, to load balance across your nodes and so on. There are a couple of different ones, and they're a bit more complicated, but you've got the general gist of a service is a DNS name that you can use inside of your cluster to communicate with a set of pods. You've also got something called ingress controllers. Ingress controllers are basically services on steroids. They have the same idea of marshalling requests to different pods, but they also have much smarter logic saying that they're HTTP based. So they can say, if you go to /x, you should go to this service. If you go to /y, you should go to this service. If you go with this header, you should end up on this service. So it's basically a way for you to come into your cluster and based on your HTTP call, get redirected to a bunch of different services inside of your cluster, which then redirects to the individual pods. So you can have this one entry point in that fans out across your whole microservices architecture internally. There are a bunch of them available. The simplest one is NGINX, which is based on NGINX, you guessed it. But there's also things like ambassador.traffic, Istio, with different levels of features. I have worked a little bit with Ambassador, for example, which is nice, because you add annotations to your pods, and then magically they get wired up into your ingress controller. So whenever you deploy a new service, you can add and say, hey, I want this thing to actually answer on this address here, and then your pod automatically gets trafficked through Ambassador for an easy deployment. Whereas NGINX requires a bit of configuration. And Istio is a whole different topic because it also rewrites your entire service stack into being a network or a service mesh instead with much more controls. It's a higher level thing than just Ambassador and NGINX. And we also got deployments. So deployments is the last sort of resource level. So we've got pods, right? And on top of pods, we put replica sets. So replica sets generates pods. We don't create pods because we don't get load balancing, the whole taking care of multiple replicas. So we have replica sets. But we have one thing on top of it called the deployment. So a deployment creates a replica set, and a replica set creates pods. The reason for this is deployment. If you define a deployment, it will create these things for you, but if you ever update a deployment, you can tell that, hey, I want to update this whole deployment here, And please do that in the way that you take down one pod at a time in different nodes over time. Make sure that they are up and running for at least 20 seconds before you pull down the next one, or take it 2 at a time, but always leave these many pods running with the previous version. So it's basically a nice rolling update throughout your cluster that you can roll back if you want to. So it gives you one higher level of control. And I'm just going to quickly show you that in here. I have a last level here is my deployment. So deployment is kind deployment. It has the replicas thing right in here. So it basically has the setting for your replica sets inside of the spec. And then, so this is your replica spec. And then inside of your replica spec, you have a template, and this is the template for the containers that you want to run for that replica set. So it basically merges, this YAML file merges your pod spec with your replica set spec with the whole deployment spec on top of it. In this case, I also want to deploy a few other things. So these things here, 3 dashes in a YAML file basically means this is a new resource, so we can have multiple resources in one file. Then I'm also going to deploy one individual pod in this case. And the individual pod is going to be a Redis pod. So you don't want to have Redis in multiple pods, because it's going to be less effective cache if we put it like that. So we want one of these. So I'm going to deploy one of those. I'm just going to use the image Redis from Docker Hub. Then I'm going to deploy a service in here, which is a cluster IP service that's called Redis. So if you go into the DNS asking for Redis, it's going to point towards the apps called Redis port, TCP port 6379. Basically, it's a service in front of your Redis cache. And then I'm going to put up a service here, but this time I'm going to use a node port. Node ports will, as I said previously quickly, they will map a random, you can select it, but let's just say a random port on each one of your nodes. So basically all nodes get the same random port, or each node, yeah. And that port on your node, which is going to be like 32,462, completely random stupid port in a specified port range, that will automatically get forwarded to port 80 on this service, which is then forwarded to port 80 on your actual node. So if I create this deployment, like that, you'll see cube ctl get all. You will see that I have now a deployment, a replica set, 3 replicas, a Redis cache, a Redis service, and a node port called web. And the node port here says, hey, I'm listening to port 32469. That means that port 32469 on any one of your worker nodes will go to that service and then port forward to your nodes, or your pods, sorry. In the case of Docker for desktop, it actually maps your local host on that port. So if I go local host on that port, I'm now talking straight into my pods. So I can go in here and have a look at my application, and we can see that it can communicate with Redis because you can see the Redis stuff. So that's kind of cool, and that allows us to basically put a load balancer in front of all of our worker nodes, and then have the load balancer load balance across the worker nodes on that port, and then internally that port will map to a service which is then load balanced across to the different pods inside of your cluster. So that's kind of one way to get into your cluster from that side. Then I'm just going to go and say, just as you can do apply F and give it a file with all of your things that you want to apply, you can do delete F, and it deletes everything defined in that file, which is nice. My cluster is now all clean. So deployment, nice way for you to handle rolling updates and managing things like that in a nice and easy way. And all of these YAML files can nicely be put into source control, version managed, and everything like they should. So you always know what's running in your cluster. If you want to redeploy something, you just run that YAML file again. So what else do we need? Well, we need some configuration. We need to be able to configure our pods to do what they should be doing. We need to be able to add storage, and we need to be able to do some health monitoring. These are kind of the main things that we need to sort out besides being able to run our containers. Configuration is fairly simple. If you have worked with Docker before, you know that in Docker we get configuration into our Docker containers either by doing environment variables, or we do volume mounts, right? So we mount files into our application and we read those files. Sweet. If we change the logo up in the corner, we're done, because we do exactly the same thing in Kubernetes. The main difference is where we store the values we put into our environment variables and into our files that we map in there. So here's an example of something called a config map. A config map is a resource in Kubernetes that contains configuration. And then you can map information from a config map into your pods using a volume mount or an environment variable. So here we have the config map, my config map, that has the data timeout, which is a string that corresponds to 5 minutes. And then in my pod, I define that, hey, I want to have an environment variable called timeout. I want to get the value from a config map key reference. The name of my config map is my config map, and the key is timeout. And then once you start this pod, it will go and look for that config map, find the value, and inject that as a environment variable. And you can also go and do the same thing with files. So you can have a config map with the contents of a file. And then you can take that content and mount it into your pod and say, whatever is in this config map, under the value config.json, please map that into, in this case, /app/config.json in my application. This is kind of nice. So you got your config together with your application where it should be. Little short demo of how that works is we look at our config map here. I have a, this is just my web, actually, let's start here. I have my config map. It has a statement, which is just a string, Kubernetes is awesome. And I have an app settings.json that sets a value like this. And then I have a web pod here. And as you can see, it does a few things. It has the environment variable name like that, set to a reference to the web config map and the key statement. So that environment variable will be set to that value. And down here, I'm creating a volume called config volume based on the config map web.config, or web config. And then I go and say, I want to mount the app settings.json thing into app settings.production.json in my application, which means that anything in that app settings.json is going to override the one that is in my application. If I've got these two, I can go out here, config. We'll do kubectl, and here the important part is that we deploy that one first, because that has to be there, otherwise it can't map an environment variable. Once that is deployed, I can go and deploy my web, and then we can say kubectl port, and that was F8, that's the one. Nope. It was supposed to be pod, web, or just web, like that. And if I go back out here and I refresh this on port 8080, we can go to configuration and it can just verify that it does say Kubernetes is awesome, and it did get configuration from Kubernetes config map in here as well, so it did read everything properly. So once again, we store our config together with everything in the cluster. I'm just going to kill this, delete -f. Actually, we can do delete. Come on. And finally, no. We'll just delete that. So config like that is quite nice. You put your config in there, and then when you're running in your dev cluster or your local cluster, your pods will just read from that specific cluster, which is quite nice. We've also got something called secrets. And I just want to mention secrets because they are the same thing as config maps, but they are secret. So the values inside of a secrets instead of a config map is base 64 encoded. That is very secret. It has nothing to do with being safe, as in secret, but you can set access rights to a secret, for example. But the whole idea of doing the base64 encoded is more of an intent, basically saying stuff in secrets should be credentials and things like that, stuff in CONFIGMAPS should not. And then it's more of a sort of intent kind of thing with the name. It's not actually safe in any way whatsoever. I would suggest getting some other way of storing credentials, like, for example, a key vault in Azure or something like that. You've also got something called image pull secrets. I mentioned that when in all of my pod YAML files, it says image pull secrets, basically saying what credentials should I use when I pull my images. And you create this is nice, right? That's easy to read. You create a pull secret by telling kubectl that I want to create a secret. It's a Docker registry secret. You give it a name. You tell it what server to use, username, password, and the email. You can put in whatever you want because it doesn't matter. And then those credentials are being reused whenever you try to pull an image, which can be a useful thing. Storage. Storage is basically Docker volumes with some extensions. So I'm not going to show you, but you map in volumes, and depending on your provider, you can use different types of volumes. There are a few different types. But for example, if you're running in Azure, you can take an Azure disk or an Azure file, and you can map that as storage inside of your pod. In AWS, you can have AWS Elastic Block Store, for example. So it gives you storage external to your cluster that is persistent. You don't want to store things in your pods because they'll come and go, so external storage is quite important. And the final thing that I mentioned was container health monitoring. And the way that we monitor health in Kubernetes is something called a liveness probe. So a liveness probe is, in its basic form, you can set it up to be an HTTP call to a specific endpoint in your application. And if that endpoint returns HTTP 200 to 399, all those status codes are considered I'm up and running and everything is fine. Other than that, if it's not any of those status codes, it's considered something is wrong. And then in your definition of a liveness probe, once again, HTTP GET is the simplest thing. You can do much more complex probes. But the idea is that every X seconds, in this case, every 3 seconds, it will do a probe. And whenever, in this case, it fails the probe 3 times in a row, the container is considered failed and will get restarted. And you can also tell it, I want to delay it 3 seconds. Don't start probing until after a few seconds because there's a bit of a startup time for my pod, for example. I'm actually not going to show you because I want to show you something a bit more, and I'm a bit late. The liveness probe is kind of that. All that you're going to see is basically if you turn it off, it fails. But I want to mention readiness probes as well. So readiness probes are a bit complicated compared to liveness probes, because when a liveness probe fails 3 times in my case, or how many times you have decided it should fail, it will restart the container. That's very good if your container is misbehaving or failing in some way, but not failing in such a way that your container restarts. Readiness probes it works in the same way and you define it in the same way, but instead of liveness probes, you write readiness probe. All the other configuration is the same. The difference is that if your readiness probe fails, you are not restarted, but you're being removed from a service rotation. So basically, any service that is fronting your pod will not use your pod. So basically, no calls will be made to your pod. It will be taken out of load balancing rotation, and then whenever your readiness probe starts responding proper codes again, 200s for example, it will go and plug it back in, and it will get part of the rotation. That is kind of neat because it means that if you get an overloaded pod, your pod can go and say, I have too much to do, don't send any more requests to me, but I don't want to get restarted because I'm working. Or if you have like a very long running task and you can only do one at a time, you might have many, many pods in there, and they can basically take one request at a time, and every time they get a request in, they go and say, I'm not ready, they get taken out of the load balancing, and they can do their work, and then they can come back in again. So the readiness probe is logically the same kind of request or check, but instead of restarting, it just removes it from getting more requests. Other than that, I would suggest that you go and play with it. I must honestly say I've been coding for 20-ish years now, and lately it's hard to make me think coding is really fun to the degree where I want to sit at home and play with my computer on weekends. I have other stuff to do. But this was actually kind of cool. Getting started with this, it's just so simple because you can try all of these little things, and every little thing you want to try. I want to try to put up a pod with a service in front of it. Takes you 5 minutes to do. You can do a little 5 minutes here and 10 minutes there, and then slowly you start trying all these things. And it's really quick, and once you're done, you just go and delete whatever is in your cluster, and it's all gone. So you don't have this thing of, oh, there's so much work to get started, or I'm going to leave my machine in a weird state. It's just spin up a cluster, run some stuff in it, kill whatever is in there, and then go and have dinner. Thank you all for listening.